Hello everyone. Today I'm going to talk to you about a paper called Approximate Maxwell Min-Multicut Theorem for Graphs of Bounded Treewidth. This was a joint work with Tobias, Davis, Nikhil, Ziena, and myself, Nadym, and we all worked at the Hasso Plattner Institute in Potsdam, Germany. So the problem we are interested in this paper is a generalization of the Maxwell Min-Cut problem, so let me introduce this problem first. The Maxwell Min-Cut problem is described as follows. We have a graph. It has capacities on its edges, and we have two vertices called S and T, source and sink. The problem has two sides. The first one is the cut side. So a min-cut is a set of edges whose removal from the graph separates S and T, and with minimal capacities. The flow side is basically to find the maximal flow that can be routed between S and T with respect to the capacities in the graph. Those two problems are dual to one another, and regardless of the network you choose, their values are equal. This was established in 1956 by Ford and Thordarson, and this was called the Maxwell Min-Cut Theorem, and it states that the max flow value through any network from a source to a sink is equal to the cost of a min-cut. Both can be found in polynomial time, thanks to the Ford-Fulkerson algorithm, for example. Our problem is slightly more general, and it's called the multi-commodity Maxwell and Min-Multicut problem. So we have, instead of having one source and one sink, we have multiple pairs of sources and sinks. Here we have three pairs, and the definitions of min-multicut and max-flow are a bit different from min-cut and max-flow. A min-multicut is defined as a set of edges with minimal cost whose removal would separate each Si from its Ti, and the max-flow is the sum of the flows that can be routed between each Si Ti. Here you can see that the min-cut value of this instance is 7, and the max flow is 6. So the Maxwell Min-Cut theorem does not hold anymore. Also, it is NP hard to compute the min-multicut even in very restricted classes of graphs. It's actually APX hard on trees. So our goal in this paper is to find an approximate Maxwell Min-Cut theorem for the multi-commodity case, meaning we want to find the smallest alpha possible that would satisfy this inequality. Now let's jump to related works and how our results illustrate this. So this problem has been studied for the last 30 years, particularly in KR minor free graphs and Treewidth R graphs. And our result is tight for Treewidth R graphs. Our result can be summarized as follows. Given a Treewidth R graph, one can find a fractional multi-commodity flow of value f and a multicut of capacity c such that f inferior or equal to c inferior or equal to beta of log r plus 1 times f in polynomial time. And we provide an algorithm for that. In our paper, we suppose that on top of the graph, we also have its tree partition. It is possible to compute from any given graph its tree decomposition. Its tree decomposition is just some structure that will tell us a bit about how similar to a tree the graph is. The tree partition can easily be obtained from the tree decomposition by just giving numbers to each bags, giving the number as index to the vertices inside each bags, and then connecting the vertices that have the same name but not the same index that are in successive bags. Successive meaning one is a descendant of the other. This in turn will give us a graph in which every edge is situated either inside a bag or between two successive bags, and we will heavily use this for our result. Our result also heavily uses the linear programs of the multi-cut problem. So here on the left you have the Maxwell problems linear program, and on the right the min-multicut linear program. Let's decipher a bit what this linear program on the right means. So we want to minimize the quantity of the capacities of the edges that we choose. X of e is our decision variable, and it can take values either 0 or 1. And this constraint in the middle just means that on any path between Si and Ti, we pick at least one edge, meaning that those paths are all broken, because picking an edge is equivalent to just removing it from the graph. If we relax this problem, we then get something completely different, because now what this means is that every edge will not necessarily be removed, but rather it will have some weight between 0 and 1. And if you look at it closely, it also means that the constraint on top is very different, because this means that by adding up the weights on each of the paths between Si and Ti, you get a value of at least 1. Let's look a bit closer to what an optimal solution X star would look like. Actually, a solution X star would be a mapping between the edges and 0, 1. And with that constraint that is in red right now, with this constraint, we would have the very cool feature that by using X star as a distance function in our graph, we would have a distance of at least 1 between any Si and Ti, which means that we would have a lower bound on the distances between Si and Ti for any given I. Let's continue and we'll see how this comes in very handy for us. So that everyone gets a feeling of what a multicut looks like, let me also introduce how I will represent graphs during the presentation. So my graphs will be circles and the vertices will be points inside this circle. Also, my cut edges will always be those green lines. And here you can see that the green lines are indeed a cut, because every component in the graph, so this would be a component, this would be another component, and this would be another component, etc. In each of my components, I cannot see an Si and Ti in the same place. Here, on the contrary, I can see that S5 is in the same component as T5, and S2 is in the same component as T2. So those green edges are not a cut. And again, this would be a cut. Like I could basically just separate only my SIs and I would have a cut. So now, remember in the related work slide, I had my first line was a paper from 1996. It was from Garg and al. And it's basically the region growing. And this paper described the region growing method. And I'm going to describe it to you again today. So I have my graph and my multicut instance problem instance, and I have some length on the edges. I will replace those lengths by X star, the solution to my relaxed linear program, as I explained 2 slides ago. I can then have this property, very interesting, that any given path between Si and its Ti is at least of length 1 with respect to the metric X star. And now if I run this algorithm here, I will have a multicut, but let's run it to convince everyone. So I select S1 here, I choose a radius randomly between 0 and 1/2. I cut those edges, so remember that now my cut edges can also be those dotted lines. And I create the shadow of radius 1/2. This shadow is not random, this shadow just shows how big this cut could have been. So see, Ri is chosen between 0 and 1/2, and the shadow is directly 1/2. So basically, this Ri that started in S1 here and went into here, somewhere between 0 and 1/2, could have been as big as this. But yeah, so the shadow is basically just as big as the cut could have been, in theory. And now I will continue. So S2, I create a cut, I cut it, I remove everything, I store the cut edges, and I initiate a shadow of size 1/2. I do the same thing with S4 because I don't have to take the SIs in any particular order. I initiate my shadow, S3 again, and now I have a multicut. And now what I want you to notice is that the region growing scheme can be generalized with this statement. So let L be the number of shadows that can contain a given vertex, then the associated region growing scheme yields a theta log L+1 approximation for the multicut problem. So here, as you can see, all the shadows, and we had at most k shadows, contain all the same vertex, here called S5. And hence, the region growing scheme has a log k+1 approximation ratio because at most it creates k shadows because it has k terminal pairs, and those k shadows can all intersect in one vertex. We will see this more deeply at the end of the presentation when I will convince you that our result holds. So now 2 more definitions to go and we will be ready to go to the algorithm of the paper. So small diameter decomposition is just a subset E prime of the edges of the graph, so that when they are removed from the graph, we are left with components with small diameter. Small diameter meaning that any 2 pair of vertices inside any of those components would have a distance less than beta between them. And we are going to talk more particularly about weak small diameter decomposition in our paper, because we could actually use the edges that are cut in our small diameter decomposition to create that path of less than beta between those 2 edges. Yeah. Please here notice that if beta is set to 1 and we find a small diameter decomposition in our graph with our ST pairs and with our distance function being x star, then we have indeed a feasible multicut, because there exists no path between any SI and its TI that is shorter than 1. So if we set beta to 1, every SI to NTI will be in different components of the graph. So finding a small diameter decomposition with respect to x star, the solution to a relaxed linear program of the multicut, means finding a multicut. The last definition before going to the algorithm is a lemma. It's the center point decomposition lemma, and it goes as follows. Let's say we have a set S of vertices in the graph of size at most R, which has the following property: for all vertices of the graph V and any element S of S, then the distance between V and one element of S must be less or equal than 1/4. If we have this set S in the graph, then we can find E prime a small diameter decomposition with cost in theta of log R, basically. R being the size of the set big S. Now that we have all the ingredients to see how the algorithm works, let me give you an overview first. So we have our graph G, we have capacity on the edges, and we also have length on the edges. We get our multicut instance with our SI-TI pairs placed as follows. And from that, we can get our x star function from the relaxed linear program. And we have this opt value that is basically just the value given by the relaxed linear program. And this is our optimal multicut, right? We can then starting now, we can completely disregard our SI-TI pairs, because regardless of where they are, we are going to find a small diameter decomposition with beta equal 1, and hence make sure that no matter where they are, they cannot be in the same component at the end of the procedure. Okay? So the first step to get that small diameter decomposition is to find center points, what we call center points in the graph. So they will come of batches of at most R, and for the rest of the representation, R will be set to 4, and everything will happen with R equal 4. Then we can grow regions around those batches and separate them from the graph with those cut edges that are dotted lines, purple dotted lines. We call this cut x2 because it happens in phase 2. And then we will use the center point decomposition that I just talked about to divide each of those purple regions into smaller regions of small diameter, namely a small diameter with beta equal 1. And then in any of those subcomponents of the graph, we have the guarantee that there are no SI and its TI living in the same subcomponent. And this in hand, we prove that the cost of x2 plus the cost of x3 is at most 136 times log R plus 1 times the optimal solution. So now let's jump straight to the algorithm and see how it happens. Now that we've seen the overview, let's tackle phase 1. So the goal of phase 1 is to cover all the vertices of the graph. So for this part, we will need 2 elements of vocabulary, which are center and cores. I will show you in a second what those means. So here you can also see the pseudocode, and let's go through the first iteration very slowly. So in the first iteration, we mark all the bags of T prime as unvisited. T prime is defined as the remaining tree with bags that are not fully covered yet. And while there is an unvisited bag in T prime, then we just pick the highest bag B and we make it a center. See this dark red? It's the color of the centers that are created in the first iteration of our algorithm. Our algorithm in phase 1 goes in at most R iterations for the simple reason that going downward in the tree, we grow a ball of size A being a real number, around the center. And this is our new core. And we mark all the bags of T prime that intersect the core as visited, meaning that in phase 1, we will have every bag having at least one of its vertices taken away. And since our bags are of size at most R, we have at most R iterations in this phase. Okay. Let's continue. So now we still have bags that are unvisited by our first phase, the red phase. So we create our new center in the highest not covered bag. And again, we grow a core of size A around it, downward in the tree. Let's continue. We mark all the bags that are not fully colored as unvisited. We take the highest one, we color it, we add a core around it. We add a core around the center. And again, we insert the center in the highest unvisited bag and a core. Third iteration, those are the bags that are not fully covered yet. The highest one gets a center. We grow a core around it downward. And again, we reiterate this process. And we finish with our fourth iteration, the orange one here. And it has nowhere to grow a core because it's the most down bag. So we only have a center for this orange guy. Okay, now we finished phase 1. Let's see how it looks like from the perspective of the graph, because in phase 2, we will look at the graph. So let's recapitulate quickly what phase 1 did. So you have the tree on the left and the graph on the right, and you have your centers and your cores being created in the graph as follows. And in the end, you just give them an ordering that depends on their position in the tree decomposition and not in their order of creation, right? So I give them indices now, and this core is called R1, this one is R2 because it's here, this one is R3 because it's here, this one is R4 because it's here, etc. So I do not care when they were created, I only care about their position in the tree decomposition, and this is very, very important. So new element of vocabulary in this phase is shadow. We will create shadows, and if you remember, when I talked about the region drawing scheme, I mentioned the word shadows. So the goal of phase 2 is to partition G into components S that have each a set of vertices Y that is close to every vertex in S. Okay? Let's see the pseudocode of this. So we gave our top-down ordering of the cores. Okay? And now from 1 to P, so our P cores, I will first process R1 by creating a shadow around it. The shadow has size between 0 and B minus A, meaning that the furthest most points in the shadow are out at distance B away from the center. We pick something between those two, the core and the shadow, and we cut it. Okay? And we reiterate this process with R2 here, shadow, somewhere between the core and the shadow, and we cut. Again, R3, shadow, we pick a value between the core and the shadow, and we cut. And as you can see, R4 got some of its center stolen away, right? This will not pose a problem, and we will treat this in phase 3. You will see. R4, we grow a shadow again, and we only in this direction because it only has those center points still. And again, we continue R5, R6, R7, and we have all our S components of the graph that are completely independent. Okay. We also have created shadows, and I will show you after phase 3 how the shadows only overlap a certain number of times. Okay. Now let's go to phase 3, and this is where the small diameter decomposition really happens. So before, in phase 2, we only cut roughly areas of the graph. And now in phase 3, our goal will be to cut those areas into sub-areas, basically. Okay? So we consider our set of components of the graph, S1, S2, S3, etc. till 7. And let me show you quickly what this E of yi means. So basically, during phase 2, we damaged our centers sometime. Like S4, remember, the center here was damaged, and we will need to create those edges to recover from the damage. Those edges don't mean that they reconnect the missing center points to the component, to their component. Okay, let's see what happens during this phase. So S1 starts, we process it, so we have this set, those points called y1, and they have indeed the property, because we picked in phase 2 b equal to 1/4, they have indeed the property necessary to use the center point decomposition. So we can use it. We use it and we get this small diameter decomposition with beta equal 1. So inside this component, we know that it has subcomponents in which no SI and TI can live together because their distance is too big. We continue, we have S2, it has a center y2, and they have the same property again, that they are close to every point in S2 up to a distance 1/4 with respect to x star, the metric we defined earlier with the linear probe. We continue, S3, same. And now something interesting happens, because remember, when we processed S2 and S3, we stole away some of S4's center. So to deal with that, what we will do is that we are going to see what happens here. We are going to recreate the edges that are missing. So we get again those vertices that we lost, and we reconnect them with artificial edges that we call EYI. So E here it's called EY4. It's a set of edges that reconnect this point and this point to every vertex that is in S4. And now we don't need to look at S2 and S3 anymore. We just have those 2 points that are reconnected and that exist, and they are a distance at most 1/4 from every point in S4, and we can use our center points decomposition. And now we can continue peacefully with S4, with S5, S6, and S7, and now it's done. So to recapitulate, in phase 1 we covered all the vertices of the graph. In phase 2 we separated the graph in separate components, and as in phase 3 we cut each component into small diameter decompositions, ensuring that no subcomponent contains one SI-TI pair. So now we're going to bound the overlaps of shadows. Okay, so we'll try to answer the following question: by how many f of r shadows can a vertex be covered? So we have this figure, it's the full graph, and it's very messy, and you can see that many shadows are overlapping, but we would like to know what's the worst case scenario. How many times one vertex can be covered, by how many shadows can one vertex be covered? I'm of course not going to use this figure because it would be too messy, so I will use a simpler one, and in fact I will use the tree partition of the graph to show you this. So by answering this question, we will have that our algorithm yields a theta log f of r approximation. Okay, so we run a first iteration of a first phase on our tree, and we get those three cores A, B, and C. And we have those subgraphs in yellow here. Those subgraphs have width of at most r minus 1. Because any core will take at least one, any iteration will take at least one vertex from every bag. So the remaining bags that were not fully covered by one iteration will have width at most r minus 1. So we instantiate some vertex v here, and we know that cores from the same iteration are vertex disjoint, and this will be of use now. Because this makes us realize that since we chose A and B such that B equal to A, we know that the shadow from a core cannot reach the subgraph surrounded by cores of the same iteration, which means that the shadow of A here cannot touch this subgraph, the second one, because it will be stopped by B, because the size of its shadow is the same size as this core, right? Because B equal to A. So wherever starts the core A, there's some epsilon distance here, and it will not be able to get past the core of P. So it cannot touch this subgraph. So it's protected. But so yeah, so we can also just note, since similarly to the fact that we noted f of r being the number of shadows that can cover the vertex coming from the whole graph, we will note that f of r minus 1, the shadows that can cover the vertex coming from inside the subgraph. Here is written edge, it should be vertex. So the shadows that cover this subgraph, the vertex in this subgraph is fr minus 1. Okay, so now let's say we have two cores in this subgraph, and I'm going to tell you that I'm going to show you quickly how only the shadow of a core that touches the core B, so the superior core to the subgraph, can reach the vertex inside. And still because of the same property that B equal to A, so to be able to have the shadow enter this part of the graph, so this subgraph, you have to be crossing B, and B can only be crossed by at most R square cores. Why? Because B has R elements, and in each iteration it can only be crossed by R cores, and there are R iterations, so it's at most R square shadows that come outside of this subgraph, so from the previous subgraph, that can cover this vertex. And so recursively we can say that f of r is at most f of r minus 1 plus r square, so f of r minus 1 being the shadows that can reach this vertex from inside, and r square are the shadows that can reach this vertex from outside. And so we have recursively f of r is lower or equal than r cubed. And to conclude this presentation, I thank you very much for your attention. And to conclude this presentation, I'm going to recapitulate quickly our result. There exists a polynomial algorithm to have a small diameter decomposition with an approximate ratio, with an approximated ratio in theta of log r plus 1. This can solve the multicut problem, for example, as I showed you right now, but also other problems such as the sparse partition problem and the universal TSP. And an open question that we've been working on is, can a method be found to get an O of log r approximated algorithm for the Maxwell Min-Cut theorem for KR minor free graphs? Thank you very much. Bye-bye.